All right. Okay, so we said that, we used, over the last couple times we've met and talked about this stuff, we said that we can use linear approximations to estimate values of functions, right? And like we did some stuff, we've gone through a couple examples where we estimated like a square root function. Like we want to be able to estimate, if I'm trying to calculate the square root of 16.3, right, I could say, okay, well, that's pretty close to 16. And so I could take the function f of x equals the square root of x and quickly do a simple linear approximation of that function using calculus, right? And come up with some linear approximation that I could use to estimate what the square root of 16.3 is. And it's pretty accurate, and it's very quick and easy to do. With a little practice, you can even get to a point oftentimes where you can make a pretty good estimate just in your head and really impress people at geeky parties. So today we're going to look at something different. We're going to look at the differential part of this. Quick review of what we talked about last time. Really, differentials, you can sort of think about differentials as just being a different form of a derivative, right? The differential form of a derivative, instead of writing it as dy dx equals f prime of x, we're really just going to algebraically multiply each side, clear the fractions, and multiply each side by dx. We're just going to get dy equals f prime of x times dx. That one simple notational difference really lends itself to applications. So then when we're trying to when we're making a differential approximation, we can, like, let's look at this example down here. So if we identify a as a convenient value of x, the actual change in the function is going to be sometimes difficult to calculate when we move slightly from our convenient value of x, right? But the linear approximation frequently is very easy to calculate at that point. Okay, so we're just taking advantage of the fact that the actual change in the function delta y is approximated by the change in the linear approximation, which we're going to call dy. Okay? And so let's start off by maybe just approximating the change in some force function acting between two charged particles. So we're looking at the electrostatic forces here that are acting. If we were to increase the distance from 23 meters to 25 meters, what would the approximate change in the force be? Okay. So here's our function, right? Let's rewrite this. So force as a function of distance, R stands for distance. Yes, sir. Your question, Seth? Oh, you're just stretching. Okay, I was pretty quick with that though, wasn't I? Right on top of it. Okay, so it's an inverse square relationship. That's the way a lot of forces work in physics. So if you double the distance, you decrease the force by a factor of 4. Okay, so there's our function, f of r. If we differentiate that, we would just, now if we're going to differentiate that, what would we do? We're not going to use quotient rule, right? It would work, but it's very clumsy. What would we do to differentiate that? Yeah, right. We just write it as 0.01 r to the negative 2 and just use the power rule, right? So what's that going to give us then? What's f prime of r going to equal? Yeah, right. Negative, I'm going to bring the negative 2 down front. Negative 2 times 0.01 is negative 0.02 r to the negative 3, which just puts the r cubed on the bottom, right? Okay, good. So now we'll take advantage of that, and we're going to estimate. We want to calculate, estimate. We're going to estimate the change in the force as x goes from, or r, as r goes from 23 to 25. Okay, so we could say another way of expressing that would be to say the change in r, which we're going to call dr, is just equal to positive 2, right? R changed by 2 from its initial value of 23. Okay. And so we could estimate the change in the force is going to be estimated by dF, right, in our differential. Okay, and what's the definition of dF here? Like we said, remember when we were dealing just in general with x's and f of x's, we said dy is equal to f prime of x dx, right? We just multiplied the derivative times dx. So how's that going to translate here? What's dF going to be? Okay, that's going to be, instead of a dx, we're going to get a dr, right? That's the input variable. What's this going to become? Instead of just an f prime of x, usually we're just dealing with y equals f of x. This time we're not though, right? This time we're dealing with the function is defined differently. The input variable is r and the output variable is force, capital F. So what's that going to become? Instead of, f prime of r, right? It's going to be f prime of r times dr. And what's the r value that we're going to plug into our derivative? What's going to go? I want to know what's going to go here. Is it going to be 25 or is it going to be 23? I get why that's a little confusing. It almost seems like it should be 25 because that seems like a rounder number. But no, it's 23 because it's the value that we started with, right? We're starting with the initial value, the force as r changes from 23 to 25, there's going to be some corresponding change in the force experienced, right? So we want to know as r changes, what's the approximate change in the force? Well, what's always going to go here is the initial value, right? So this is going to be a 23. This is like, 23 is like our value of A in this case, because that's what we're starting with, okay? So we're going to get, this is equal to f prime of 23 times, now how much did it change from its original value? 2. Okay, so we're just going to multiply that by 2. Okay, so what's that give us then? Well, we already calculated the derivative. Here it is right here, right? So this is just going to give us f prime of 23 is negative 0.02 divided by 23 cubed, right? Times 2. So that whole thing then is just equal to negative, if I multiply negative 0.02 times 2, I just get negative 0.04 divided by 23 cubed. Well, what is that? If we do that stuff. I mean, here, I think I erased it, but we'll do it in Desmos. Negative 0.04 divided by 0.04 divided by 23 cubed gives us that. They want us to round to 2 decimal places using scientific notation. So what's that going to give us then? If we let's see, I got 1, 2, 3, 4, 5, 6. I got to move the decimal place 6 places. So I've got negative 3.3 times 10 to the negative 6 because I had to move the decimal 3 places to the right. Everybody good with that? Okay. Let's try another one. Okay, how about okay. So this time, let's say we've got a metal plate where X is equal to 12.5 centimeters initially. And when we heat the metal plate up, the metal expands and it grows to a side length of 12.7. Okay, let's use differentials to approximate the change in the area. Okay? So we want to approximate delta A by the differential dA. What's dA? So the input is X, the output is A. What's the area function A of X? X squared. Okay, so A prime of X is just 2X. Okay. So what's the kind of the formula going to be for our differential here? Write the differential down without plugging any numbers in. What would it be? Yeah, it's just going to be the derivative times the derivative of X in this case, whatever the derivative of the input, which is X, right? And how come? Because normally we would say dA dx is just equal to A prime of X. That's the definition of the derivative, right? So to write it in differential form, we just multiply both sides by dx. Everybody give me thumbs on that part so far. Okay, good. All right, so what's the value I'm going to be inputting for X here then? Yeah, because that's the initial value, right? Here's my initial value. And what am I going to input for dx? Let me see that. It's growing by 0.2. That's how much the input's changing. And so we can do this pretty easily then. We end up with 2x is my derivative, so I'm getting 2 times 12.5, which is just 25, times 0.2. Well, what did we do that in our head? What's 25 times 0.2? Okay, 5. There you go. So it increases by 5. And what would the units be for area? Okay, so a change in area would be measured in units of area. So there we go. Now, if we wanted to keep track of units, we always, in math, we get lazy and we suppress that. Suppress the units. That's our convenient way of being lazy. But really, those are measured in centimeters, right? Everybody get that? Because I'm inputting a value of X, which is in centimeters, and the change in X is measured in centimeters. So it works out. The units multiply to square centimeters. But you don't really have to include them in the calculations. You just got to make sure when you think about it, well, what would the units have to be based on what we're given, square centimeters, okay? All right. So let's look now at another application. So this is the same thing, but we're applying it differently. So we know that when we're actually measuring things, there's going to be some measurement error, right? When we're measuring the length of a plate, we know that we can only measure it so accurately. Maybe it's very accurately, but there's going to be some uncertainty there, okay? So we could think of the error in making a measurement of, like in this last case, it would have been, for example, measuring the side length, right? We're going to calculate the area based on the measurements of the side length, agreed? Okay. So if we can measure these to within a certain precision, then the uncertainty is going to be equivalent to how much X is changing. It's not physically changing this time. We're not heating it up and it's expanding, but we're saying when we make a measurement of 12.5, let's just say, I don't know, this would be pretty crappy measuring, but let's just say that the uncertainty is plus or minus 0.2 centimeters, okay? The math would have looked exactly the same, almost exactly the same. We would have said, okay, 12.5 is the value we measure. We've got this plus or minus 0.2 based on measurement error. So we want to know, what's the potential propagated error going to be? We know that if I plug 12.5 in, I'm just going to get 12.5 squared is the area. That's easy to calculate, but there's some uncertainty in the measurement. What if our measurement is a little too big? Well, that's going to mean that the area is going to get, that propagated error is going to end up with a larger area, isn't it? Right? If we measured it and we were inaccurate and it should have been a little smaller than what we measured, let's say, then that's going to mean the area, the calculated area, would have been a little bit smaller, right? Now we know that calculating, well, I won't say too much more about that for a second here. Okay, come back to that idea, but let's try calculating some propagated error here, right? So in this case, small changes in the input are represented by delta x, so that's the measurement uncertainty, and we're going to approximate delta y with dy, where y is the output, right? Delta y is going to be the actual propagated error. We're going to estimate that with dy. Okay, so I'm going to read what I had here. Okay, I think we said all this last time. I don't think there's anything else I need to really emphasize. Let's try this example. This is what we started doing last time. So if we take the example of a cube this time, whose side length is 5 centimeters, and let's say that we have an accuracy of plus or minus 0.1 centimeters. We want to calculate what the potential propagated error would be. Now, I want to make a point here that the actual maximum propagated error we would find by comparing the volume calculated at 5, our measured value, with the volume calculated at 5.1, if we're off if it's actually 0.1 bigger than what we measured, and via 4.9. What if we overshot and it's actually 0.1 smaller, right? This is not a linear relationship though, right? Did everybody see that? Because the function here is going to be x cubed for calculating volume. The amount of propagated error is going to be different if we overshoot compared than if we undershoot. And so if we wanted to do a really rigorous analysis, we would have to calculate the volume at 5.1, calculate the volume at 4.9, and see which one changed the error by the most, or changed the calculated volume by the most, and that would be our maximum propagated error. That's kind of a lot of stuff to do though, right? So instead, we could do a quick and easy approximation using differentials and just get one number very simply, rather than having to go through and compare all these other calculations, okay? So what's it going to look like here then? Right, we know that the change in volume, the propagated error, is going to be approximated by dV. Well, that's just going to be v prime of x, and we're going to pick, our value of a in this case is what? What's the value we're going to plug in? Everybody see it's going to be 5, right? Because that's the measured value, right? It's like the initial value last time, right? Times dx. What's dx? Everybody could show me it's point what? Show me fingers. 0.1, good. Okay, it's 0.1. And it could be plus or minus this time. We don't know if it's going to be bigger or smaller, right? So when we plug that stuff in, if v of x is x cubed, then v prime of x, that's just 3x squared. That's easy to calculate, right? So we're going to get v prime of 5. That's just 3 times 5 squared. 5 squared is 25. That's easy. That's 75. Times dx is going to become plus or minus 0.1. What's nice is we can just do one simple calculation that's going to include the plus or the minus possible propagated error. And we just get 75 times 0.1 is 7.5. And the logical units of volume, if we're measuring side length in centimeters, well, that's going to be centimeters cubed. Okay, everybody see that? It's pretty easy, isn't it? I mean, that's an easy way to get a very simple approximation, and this is the way that engineers do it, I promise you. When you're just trying to, you're trying to do your initial calculations, it's so easy to do it this way that's how we do it. Give me thumbs on this. Okay. All right. So the other part then is we want to know how good is this, right? How good is it acceptable? Okay. Do you see, like, if I were measuring a board, and let's say the board were 25 feet long, and I'm plus or minus, let's say I'm measuring it to plus or minus 1/8 of an inch. Is that pretty good? I mean, it seems, yes, that's a subjective question, but that seems all right, doesn't it? For a 25-foot board, 1/8 of an inch is not that far to be off. Now, what if I'm cutting a board that is 4 inches and it's off by 1/8 of an inch? Doesn't seem as good, does it? Doesn't it seem inherently like that's worse? Yeah, because the measurement error is a larger proportion of the actual measurement, right? And so a lot of times when we want to know, okay, how acceptable is this? We think about it in terms of a relative error, and we've kind of had a little bit of exposure to this already. So the approximate relative propagated error is going to be calculated by taking the propagated error measurement divided by the original output by volume in this case. So dV over V, right? So in the case of measuring that board, 1/8 divided by 25 is pretty good. That's a pretty small number, but 1/8 divided by 4 is that's not so great, right? As a relative quantity. So what are we going to get here then when we're trying to calculate our relative error? Okay, so we got dV over V. Now what we could do is just plug the numbers in there, right? We know that dV, we already calculated that. dV is just going to be V prime of x times dx. That's just our differential, isn't it? That's what we had right here, right? I could plug in x equals 5 and dx equals plus or minus 0.1 and get an answer, but don't. You can simplify this always, right? I can take this dV over V and I can algebraically make this a lot simpler and more meaningful. I could divide top and bottom by x squared, and that gives us something that communicates a little more information, right? I get 3 times dx over x. Okay, well, what is dx over x, by the way? I didn't write that here, but what is that quantity? What does that represent? Right, I could think of this as being 3 times that. What's that? What's dx over x? If dV over V is the relative propagated error, the relative error, right? What's dx over x? Well, that's kind of what dV over V is the error, the relative error in the approximation, right? Because think about it, V is a calculated quantity, right? We're calculating V from x, from the side length. Agreed? And so we're propagating some error there. And think what propagate means. Propagate means you're going to pass on, right? You're going to pass it on to something else. So we're passing on this error through our calculation, through our measurement error. We had a measurement error of plus or minus 0.1, right? Produces a propagated error of plus or minus, well, whatever dV was. And so we're comparing, this is a relative propagated error. What's that? What does x stand for? Well, I mean, but what is x in our problem here? It's, okay, the side length, right? So it's the dimension that we're measuring. We're measuring, right? And dx is our measurement error, right? So do you see that this is just the relative measurement error? Dx over x? Everybody get that? It's the measurement error compared to the actual measurement. So that's pretty interesting that we're able to do that then. We're able to make see some relationship here. We end up with our propagated error is equal to 3 times our relative measurement error. Okay, that's pretty interesting to know. So whatever our error in measuring is, it's going to get 3 times worse. The relative error is going to get 3 times worse when it gets propagated through that calculation, right? So if I had a 1% measurement error, I should expect a 3% propagated error, right? And then if I want to do the calculation, once I get it down to here, all I need to do is plug in my value for dx, which is just plus or minus 0.1. That's my measurement error, right? Divided by x, which was 5, and we get 6%, okay? So what would you tell me without even thinking about it here, what would our relative measurement error have been? 2%, right? Would have been plus or minus 2%, which makes sense. 0.1 out of 5 would be 2%. 0.1 is 1% of 5, isn't it? Or 0.1 is 2% of 5. There, I said it right finally. Okay? Thumbs. Okay, let's try another one.